All right, any other question? Okay, so let's get started with our lecture. So we were talking about the spreadsheet modeling. I'm gonna go share a screen with you. Okay, so it is important for us to talk about the spreadsheet quality. That means that how to make a quality model in Excel or a spreadsheet, in short. So the topic that we're going to go through today is based on these three references. An article by Philip Bewick in 2005, How Do You Know Your Spreadsheet is Right? And another article by John Raffenperger, I don't know if I pronounced that correctly, New Guideline for a Spreadsheet. And let's just start. Hopefully this will show you the animation. Did the animation work? Do you see just the title right now, the topic?
Yeah. Yes, we just see the title.
Okay. All right. I didn't want to show you too much of the each page, so going line by line. All right, so why do we need to have a spreadsheet quality modeling? There, of course, the first thing that comes to mind is error that you can make in spreadsheet modeling or any other type of modeling. But here we are talking about Excel, so we're going to focus on making errors in Excel. As you might have had experiences with Excel, it's very easy to make mistakes if you're working with a lot of data and even simple models, you could just make mistakes. So there has been a study, rough study, they have estimated that any cell for Excel, there is actually a 2% chance that any cell can be error-free. So that means that if you are working in a spreadsheet that has, in a model in a spreadsheet that has, say, 35 cells, so the chances for your model to be error-free is 98% for each cell, power 35 cell that you have. So that's less than 50%. So there is actually more than 50% that your model in Excel is error-prone or contains an error. Okay, so as you see here, the numbers are not promising. So that's why we need to have the standards and convention and be careful when we want to develop a model in a spreadsheet on Excel. Or this is just a course and we are using this to learn to do this, but actually a lot of companies do the spreadsheet modeling and these errors that we mentioned here for them has caused, in some scenarios, they have caused problems, huge problems for them. Economic catastrophe sometimes. So for example, a cut and paste error costed TransAlta $24 million when it underbid an electricity supply contract. Another example, the falsely linked spreadsheet at Allied Irish Bank permitted a fraud totaling $700 million. And another example, a missing minus sign. So that's a small error, but very important one. Caused Fidelity to overstate their projected earning by $6 billion. Right? So that means that we should be careful if you're using a model for decision making about economics or important decisions. So that's why it's very important to follow good spreadsheet practices. We mentioned some of that, the conventional standards for using cell styles for inputs, outputs, calculated cells, decision variable cell. But there are more actually that we can use those conventional standards to help us hopefully be error-free or minimize the error the chances that we could make an error. So the general philosophy, before you start modeling and using Excel to do a spreadsheet modeling, as we said it before, think before you want to have a roadmap, what you want to do. So it's very good to have actually the influence chart that you mentioned before just jumping to the modeling in Excel. Sketch out how you want a spreadsheet to look like. So it's not just that you want to have a working model, but you want to have your model to be readable and also transferable to other people. You'll be able to communicate with other people, perhaps in a group or in a company, or even for yourself. You might have had this experience that you have created an Excel for whatever reason, for example, for budgeting, and a couple of months later, when you come back to it, you kind of lost because you don't remember everything about that document. So it's very important to make it readable. And you also need to have in mind from the beginning of modeling, who is your audience? Who's going to use this spreadsheet? Okay, that's very important, right? And also make your model as simple as possible, but not simpler, right? This is a very popular phrase, but it also applies in spreadsheet modeling. So break complex calculation into a few steps, make it readable, more understandable. And also always plan to have your first draft as a throwaway. That means that you just make a model that works and then try to make another one that is not only working, but also is readable. And it follows all the convention. It has all the standards, follows all the standards. So you can build always a prototype and then revise it and make it better. So how to make a spreadsheet models more readable or easier to understand for other people? Of course, you're gonna you should use text and labeling without having the any mistake or grammatical mistakes or errors in your description. That would be counterintuitive, counterproductive. Actually, you want to have a description for your model, and you make mistake in the description. You can use color and formatting, but only for the sake of the model to be more readable. Do not use too much formatting and too much color. Do not make color or formatting as a decorative method. Again, you should try to make your model as simple as possible to be able to understand for people, to try to use, for example, name ranges, range names, so that when you're using references to other cells, it would be easier, instead of just having B12 multiplied by C13, to use the labels that they have, the name range names, what they stand for. Right, so try to make your spreadsheet more readable, more concise, and more informative. So we're going to talk about these here. So try to organize your spreadsheet and your model based on the logic, business logic that the problem that you're working with. So use the terminology that is popular and standard in your organization. And either try to make the model left to right or top to bottom. Sometimes we might have to break this rule, but generally we try to follow this, right? This convention. Also, if you have formulas, a model that uses different formulas, different cells, try to put them close to each other, right? So do not have one cell referencing row 13 and another row 100. Okay, if it's possible to put them close to each other, try to do that. if you remember, if you click on for any formula, if you click on the formula bar, it's going to highlight the cell that is referenced to. So try to make your model such that if you click on the formula bar, you can see all the highlighted cell in one view. You don't have to scroll down or left or right, okay? So each numeric cells should start above or on the left side. And also try to document your model. You can use actually the insert commands. So it's on the review. Let me show you here. You don't know where it is. Share this with you. File. So on the review, there is the comment section and there's a new comment. So for example, I want to leave a comment here, and then you just click it and you would okay, this is where the formula is. Blah blah. Okay. So try to use these comments and review all the notations, or you could actually highlight a cell and put text in it. Back to picture quality. You could also, it's a good practice actually, if your model is pretty complex, try to add a new sheet, and in that sheet, describe the model. Give it a little description of the model, the relationship between inputs and outputs, and for example, your decision variables, etc., etc. That would really be helpful. For example, if you shared your model with someone else, or if you come back to your model sometimes in the future that you would have forgotten about your model. So how to make a concise spreadsheet? Okay, so try to put your model, if it's possible, to put it in just one sheet. Okay, so that means that, okay, try to use not too much spaces between different segments of your model, the input, outputs, the decision variable. So I would just put 1 or 2 space between each segment. So try to put everything into one sheet if it's possible. Sometimes it's not possible, because multiple sheet would make it difficult to, of course, understand the model, to find the relationship between the different parts. And also, some functionality of Excel doesn't work when you have multiple sheets. For example, the formula, when you want to use the auditing tools for formula, it doesn't work if you have different parts in different sheets. Use some blank space to make it each segment different, but do not use too much of it. Do not use unneeded cells. For example, you're developing your model and somewhere you realize, okay, you need to compute something, a number. Then you find a little cell somewhere in the right side in the sheet, and then you type something, you compute something. Don't leave it there, okay? After you used it, try to delete and eliminate those, because you might have seen actually those if you're not careful about it. When you come back to it later, or if you give this spreadsheet to someone else, it's going to make them confused that, okay, what is this? What is this, and what is the relationship between this computation and the rest of the model? Okay, so do not use the unneeded cells, or try to get rid of them. It would be clutter otherwise. Avoid labels that overlap neighboring cells. That doesn't make it to be able to see it. And also align data types in a consistent manner. Okay, so always try to be consistent. For example, use the left cell for the label, or put the label above a column. Okay, try to be consistent as much as possible. And if there is a part of the model, again, that you use for computation, or some other things that do not have to do anything with the model. It's kind of irrelevant. Just get rid of it, okay? Erase it. So how to make an informative spreadsheet? Again, use description. So commenting, putting labels, and also just using label inside the Excel sheet. But do not use the description for decoration, just like using different colors or different fonts or different type of different size of fonts. So anything that you do in this system, it should be helpful for describing. It should be descriptive, not decorative. Okay. So anything that you do, again, after you're done with it, try to evaluate. Okay, why did I do that? What does that color mean? What does that color mean? Or what is the that bolding mean there? If it's just for decoration, then it shouldn't be there. So a good thing that we learned, a convention that we used was my style, that we use the inputs, my inputs, blue color. We used red for decision variables, the blank one for calculated values in the middle, and also we use the gray, or in my case, yellow, for the output. Use format, do not use format too much. Again, if you have, we use just 4 colors, but if you have like several colors in one spreadsheet, in one sheet, it would be confusing. And so instead of being helpful and descriptive, it would be confusing. All right, so only one type and one size. So we said that. So avoid multiple styles at this. Use multiple styles at the same time. So for example, bolding and making this the same sentence or word on underscore, having underscore. Okay, so one of them is enough. Okay, sometimes I have seen myself doing that in the Word file. And also avoid using multiple colors. Okay, so every formatting that you do, it should be for the description reason. It shouldn't be decorative. All right, also expose information. That's a very good practice and a standard to follow. Sometimes you, for example, open up a new sheet for some other computation and you just leave it there. You forget to, for example, delete it and get rid of it, okay? And when you give that spreadsheet model or file to someone else, and he or she would try to figure out what this model is about, what is the relationship, then that sheet would be a question, confusing for them. Also, do not hide, for example, several cells or, for example, rows or multiple columns, because you're hiding information from that person and that they might not realize it. Okay, so formulas should reference cells that contain data or other calculated quantities. Also, in this manner, using range name would be helpful. So when you want to model, try to identify out of these whole many numbers that you might have, try to identify the key numbers and put them as like a input cells. Use the formatting for those. Okay. Otherwise, it wouldn't matter if you have, say, 1,000 data and all of them are colored as blue as input. Okay. Don't hide or rows or columns. This would reduce, of course, readability and also the confidence of the person that uses your model or yourself in the future. You might not realize, okay, what is the relationship here? And use labels and try to be consistent. For example, use labels either on the left or above column if it's possible. Sometimes it's not possible and you have to break this law. And also, sometimes we use like a label that is too large, so you want to use abbreviation, but try to limit the use of abbreviation, or try to use it in a way that is more readable and easier to understand. Okay. And avoid using all caps, of course. That would be jarring. So here are, I'm going to list some common mistakes here. It is possible it might have happened to you before too. I've seen actually some students do that. You're pointing to the wrong cell. Okay, so for example, in our assignment, we had a growth rate for housing prices, and we also had interest rate. But when you want to, for example, compute the housing prices in the future, instead of referencing the growth rate, you might actually have, by mistake, referencing the interest rate. Okay? So it's very possible to point to the wrong cell. So it would be very helpful if you use range names instead of, like, say, B4 that shows the I or the growth rate. Then you would just tell interest rate, or you could say growth rate. Copying and changing some, but not all of them. You copy and paste it somewhere else, and would change, for example, the first row, but forget to update the rest of it. That's also a common mistake. Referencing parts, but not all. For example, you want to use a formula, for example, a built-in formula such as sum or sum product. And when you try to select the data, you forget to select the first one, or when you drag it down, the last value is going to be left out. Okay, so these are very common errors that I've seen, mistakes. Making a temporary fixed permanent. So for example, you're working with a model, and then you try to see, okay, what if instead of 4, it was 6? And then you implement that to see it for your understanding or curiosity, or for whatever reason. You change that value to 6, but then for whatever reason, you forget to change it back to 4. Okay. Mixing units. This is also important. We actually had an example of this. So for example, remember that we said, okay, the values are in 1,000, but somewhere you forget that the values are 1,000. So instead of like putting 1 that stands for $1,000 in that column, just you put the whole number 1,000. So that would be like a million, right? So that's also like a very common mistake. Misunderstanding a function's argument. These are pretty for those built-in functions that are more complex than something simple as sum or multiplication or power. For example, we had example of that, the PPT or the net present value. So this econometrics function could have multiple actually parameters, and it will be very easy to actually miss one of them or misreference one of them, and that would make the computation wrong, of course. And that's also another common mistake. You would assume that your cell formula works properly, but it actually doesn't. For example, maybe it doesn't work for value of 0 for whatever reason, for example, division by 0, and then you ignore that, and then you apply that formula for all the values, and there is a couple of zeros there that would be divided by 0 and would end up into errors, right? Okay, so that's our guidelines for making a quality spreadsheet. It's very important also for the assignments that we're going to have, including assignment 1 that it is due tomorrow night. It's not just that your Excel model have to work properly and your computation should be correct. I'm also going to create your work based on following these conventions. How, the quality of your model. Are you using labels? You're using range names. You're using all the conventions that we have, the writer style, the inputs, the outputs, etc., etc. Okay, so I'm going to also create your work based on that, not just your final solution. Any question?
Professor.
Yes.
So I know you mentioned we shouldn't work with other classmates on our homework, but what are we able to like ask you any questions about our homework, or to?
Yeah, I had one student on Tuesday. I'm actually, yeah, Tuesday night, and two students today that came to my office hours and asked question about the assignment. So the question shouldn't be something that is just straight out the final, asking the final answer, or something that leads to the final answer. But yeah, of course, I can help with the any question that you have about help you understand the problem with it, or what's wrong with the model probably.
Okay. Okay, perfect.
Professor, I have a question about using the the define name for the name manager tool. Is it possible to turn that on by default so that you don't have to do it every single time?
I don't know. I'm not too sure, but there is like a macro file that can do that. It's like make everything automatic, but I don't think there is like a function separate from the macros that would do that.
Understood. Thank you so much.
Yeah, and also that's actually kind of a risky thing to do, because not always there is your variables or your names and labels on the left or above. Sometimes it changes, right? So I think that would be a risky thing to do.
Understood. Thank you so much.
Sure. All right. So let's go back to our lecture. We're gonna actually start a new topic, optimization. So we're going to learn about introduction to optimization. This is going to be a general theoretical introduction to optimization generally, and then we're going to move on to applying and modeling optimization with a spreadsheet model. So probably we're going to have several weeks, say, I don't know, 6, 7, 8 weeks from now, we're going to still work on optimization because it's a huge, actually, chapter and topic, very important one too, and very useful and practical. So let's start. Features of optimization. So what is optimization? You might know the name optimization. You want to optimize something. For example, you want to optimize a system, or and based on that. So here we would model that system into a mathematical model and then try to optimize it. And optimization here is based on an objective function. So it's whether, for example, an organization wants to maximize its profit, that's optimization, or it wants to minimize its cost, or for whatever other performance measures and metrics that they want to optimize. Okay, so let's learn about the different features or components of optimization models. So each optimization model has what is called as objective function, or the goal function. And what is that? That's actually the system's overall performance measure. For example, we want to, again, an organization wants to maximize their profit. Okay? They want to maximize their total profit, or they want to minimize the cost, or for example, because the staffing is going to be costly, and also you might not want to assign all the staff in an organization to make some available for other jobs. So you want to, for example, minimize the weekly staffing cost. And the other component or feature of any optimization model is what is called that decision variables. Those are the variables that we can control. That means that we can decide the value of. Okay, so those are controllable variables, and an example of that would be how much of each product we should produce or we should sell. Okay. How many agents should work each shift, okay? Or what persons with what skills should be assigned to which operation, which machines or equipment. The other components or feature of every optimization model, we actually have a type of optimization model that do not have constraints, but generally when we talk about in this course, we have constraints. Okay, so constraints are conditions or limitations on our resources that is going to impact our decision making. that we need to follow, we must do or we must not do. Things that we must do or we must not do. For example, we can't use more hours of labor than they are available, or we can't use more money than our budget lets us to do that. Okay, so these are the must and must not do, or the limitations of that systems enforces on us. And optimization is actually a huge word for itself. You can't get, for example, a PhD in optimization and learn everything. Okay? It's a huge field for itself, and it has different actually branches that many people use, and it's also in interdisciplinary science. So I've seen people in mechanical science, mechanical engineering use it for even PhDs. Electrical engineering, computer engineering, and industrial engineering, business schools, they use it. Right, so let's see different types of models. So we have several different models. A more popular one, the most popular one is generally called is linear programming. Okay, so in linear programming, which is in chapter 3, 4, and 5 of our book, textbook, which we're gonna focus on a start of our lecture with. It's where the objective function and the constraints relative to decision variables are linear. Okay? What does it mean to be linear? Anything that doesn't have a power more than 1, or it should be exactly 1 or 0. That means it's just a number, or it should be a number multiplied by a variable. Okay, so you shouldn't have x squared, or you shouldn't have x power 3 or x to the power of, say, negative value. That means that you have on the division side. Okay, so this is a simple linear formula. Total profit is equal to 20 multiplied by x plus 30 multiplied by y. Okay, so we don't have any power more than 1. We don't have any variable multiplied to each other by each other. For example, we don't have xy here. We don't have, for example, 1 over x, or 30 divided by y. So we don't have anything like that. So this is linear. Any other model that breaks this rule, it's non-linear. Okay, so any breaking of this rule would make the problem non-linear. That's another different type of model by itself. We're going to see that in chapter 7 after we cover the linear program. Okay. So a nonlinear programming model is a model that has, even for one incident, if this linearity breaks, a linearity rule breaks, that makes our model nonlinear. For example, if instead of total profit equal to 20 multiplied by x plus 30 multiplied by y, if it was 20 multiplied by x squared, then it would make our model nonlinear. Okay. So here you see a complex nonlinearity. You see 5 multiplied by x squared. So that's actually a breakage of the linearity. So this is nonlinear. Log of y, logarithm of y, that's nonlinear. 3 multiplied by x divided by y, that's also non. But it doesn't have to have, everything in nonlinearity. It's just one component. If it's nonlinear, it makes the model nonlinear. The other type of model that we have, and they're very popular, they're called integer programming or integer linear programming, ILP, which is going to cover it in chapter 6. So in these models, some of the decision variables can only take integer values. So they can't take whole values. For example, you can't have, if you are deciding optimizing staffing or scheduling for your staffing in your organization, you want to see, okay, how many staff you should assign to, what day at what part of the organization. You can have 4.3 people assigned to, part A, or 1.2 people assigned to part B. Okay, it has to be a whole integer, whole digit. It has to be 1 or 2. Okay, so that's. And the last one is called stochastic programming models, which we won't cover. That's probably one of the toughest and most complicated one. And in this stochastic programming model, what is different is some of the values are uncertain. So they are not given. They are random, okay, random values. So we are dealing with random variables, and that would make your model stochastic, okay? So you could have stochastic programming, which is integer. The model is integer. You could have a stochastic programming, which is nonlinear. You could have a stochastic programming, which is linear. You could actually have a nonlinear programming which has integer values too. Okay, so the different combination of these would make different models. All right. So what are the different steps in optimization or developing optimization model? It's the first step is to model building or formulating your model. And that means that okay, you have to specify what would be your goal or the objective function. If it's a profit, you have to formulate the profit based on the values, the inputs that you have, for example, the prices and the decision values. So you have to set up all the objective function, the constraints, the right-hand side, the decision variable, everything. What input you need to have, specify the decision variable, what sort of constraints your resource is going to enforce you. So you need to specify all of this, and also you need to understand and specify the relationship between each component, okay, the decision variables, the right-hand side, left-hand side, for each resource, each constraint, and the relation between the objective function and each decision variable or each resource. And after you have built your model, after the first step is done, you want to solve your model. Okay, you want to optimize it to find the optimized solution or optimal solution. A model solution can be feasible, can be infeasible. A feasible solution is a solution that satisfies all constraints. So any solution that just violates only one constraint would be infeasible. We could have also feasible solution. We could have feasible solutions that are non-optimal, and we could have feasible solutions that are optimal. Okay, so we can have optimal solution, non-optimal solution, or we could have also suboptimal solution. So finding the optimal solution to a model is actually a difficult task, and we have actually different methods, different algorithm to solve this depending on what type of model, what type of problem work with. For example, for linear programming, we are still using the simplex algorithm that was invented like 70 years ago. But for other types of, for example, for nonlinear programming, for integer programming, we have non-conventional actually methods that are coming out every month or every year. The solver that we're going to use, or the algorithm that we're going to use, or the method, the optimization tool that we're going to use for our courses, we're going to use actually Excel solver. So Excel solver is actually, it has different solvers for, it uses the simplex algorithm for solving linear programming. It has also some nonlinear programming tool, and also for some heuristic algorithm too. But there are other software which are more professional, more actually complex, and that can be used for a more business side problem. A lot of organizations actually use Excel solver, but as I'm going to show you, it is limited. The number of variables, the size of the model that you can build in Excel is pretty limited. It's just 200 variables, decision variables, and 100 constraints. To give you an example, actually, other solvers that you can see, Ample, Simplex Studio, and GAMS. Actually, Ample and GAMS, they are not solvers. They do not have like an algorithm by their own. They're just a language to represent your model, and then you have to use a solver to solve them. But I have used Simplex, both Simplex and Groovy, which are actually available for a college, a nonprofit organization. So you can actually get a license for these softwares. For example, I work with Groovy, And even with my laptop, I can actually solve a problem that has a medium decision variable, and that's a huge problem to think about it. As I said, a lot of organizations which are like big companies, they still use Excel if their problem is not too large. But in a lot of cases, just the number of the size of the problem get out of hand, and there's no other way to use other than the professional software. Sensitivity analysis. So after you solve the problem and find an optimal solution to your problem, your job is not done. Okay, so there's going to be an after optimization analysis, which is sensitivity analysis, which is very important because the values that you have used as inputs, as like coefficient for your decision variable, as your maximum values or minimum values for your constraints or resources, those are sometimes estimated, and sometimes it could actually change. You're not sure about it. So you want to sometimes see, okay, what if something happened? What if, for example, your one of your constraints, the resources value goes up, like say 10%, or decreases, or what if the price increases or price decreases? You know, so you can actually do this analysis with the sensitivity analysis. And it's a very important step. How does the model optimal solution changes if you change the output? So this is, you want to find the relationship between each component, each decision variable, each coefficient, each right-hand side parameter or each left-hand side parameter, and you want to see the changes in that value and the impact that it has on the output for the objective value. Right, so as I said, the linear programming type of optimization model is the most popular type of optimization model. It has been estimated that almost 85% of Fortune 500 companies, they use LP model. It's a powerful modeling framework with a simplex algorithm and other efficient algorithm. You can actually easily solve very large problems with millions of variables and hundreds of thousands of constraints. So you can actually solve to optimality very large problem using the linear programming model. And also it has application in many cases. There are several cases that I just mentioned about the staffing or scheduling of your staff, that there are certain scenarios that the problem, you cannot have for example, you cannot have decimal numbers, and that's the integer programming model. But for most of the time, you're facing with a problem that can actually work with the whole number. So you can actually use it modeled as a linear program if the linear relationship between your components in the model, the decision variable, the objective function is linear. Right, examples, different example you can see. For example, in finance, you can actually have a model to see your option for investment on, for example, for the stock market. We're going to see an example of that, a simple example of that today, right? And assess, for example, risk, because you want to minimize risk of investment, you want to maximize the profit. We have actually examples, linear programming example in logistics. For example, FedEx uses that. For example, to decide what is the optimal location for a super hubs when they have, say, hundreds of planes and thousands of trucks they want to route it there. Okay, and what is the best route for these trucks? And also for the manufacturing examples of type of problems. K-Log, for example, is an organization who uses that in manufacturing, who uses optimization linear programming. Amazon actually uses, Walmart uses LP. So for example, they want to, K-Log, they want to find the optimal solution to the problem, which is, okay, how much cereal they should produce, from each plant, and send it to what market. Right, so here we're gonna see a very simple example just to introduce you. You might have, depending on your major and your background, you might actually have been exposed or you are familiar, could be familiar with optimization, these types of problem. But here I'm going to introduce you to a very simple problem, optimization problem. It's a linear programming problem. We only have two decision variable as a few constraints, before constraints. That's going to show you how an optimization model look like. Okay, so this is a linear programming model. Okay, suppose that you have $1,000. You want to invest that money into a stock market. Okay. So you have narrowed down all your choices into just two stocks. Okay, so you want to either purchase a stock A or B or a combination of these two. So now you want to decide, okay, how much should I invest in A? How much should I invest in B to maximize your profit? Okay? So this is a problem. The problem is, you know that these are your input. You know that a stock A, based on the previous data and historical data, it sells for $4 per share and has an expected rate of return of 6% per year. Okay? Suppose that you want to see your best decision, optimal decision on investment for a year from now, for next year. Okay. A stock B, on the other hand, it sells for $6 per share, so it's more expensive than a stock A. But on the other hand, its average rate of return is higher. Instead of 6%, which is for a stock A, it's for a stock B, it's 9%. And also, you might actually have some, let's add more constraint just to show you that how constraint would work. So suppose that for whatever reason, you don't want to invest more than $700 in a stock A. And also you don't want to invest more than $600 in a stock B. So right now you have three constraints. You only have $1,000 to invest. You don't want to invest more than $600 in stock B and $700 on stock A. Okay. So now the question is, you want to find the best solution, best investment solution for you, or this investment plan. How much of a stock A and a stock B you should purchase to maximize your profits, investment profit or rate of return in a year. Okay. Right, so now we are in the first step of formulating the problem or the model. So we need to identify the objective function, the constraints for each constraint that we have, the decision variable, right hand side, the left hand side, etc., etc. All right, so what are the inputs here? The inputs are our resources, and that's the money that we want to invest. We have $1,000, that's our input that we want to invest. What is the output? The output is the rate of the return of investment after a year. What are the decision variable or activities here? How many of a stock A and a stock B we should purchase? What are the constraints? We have three constraints. Actually, we have two more constraints. There are three types of constraints. We have less than equal to type of constraints. We have greater than equal to constraints, and we have equality constraints. Okay, so in this specific problem, we actually have the less than equality problem, and that's our constraint on our budget. Okay, so that means that, okay, how much we spend on investment should not exceed $1,000. That means that, okay, whatever we spend on a stock A and a stock B, it should be less than $1,000. Okay, so we have the less than equal to type of constraint. For the greater than equal to type of constraint, we also have that. Actually, in our problem, we have to specify that to the model, because we want to solve it with the solver. You have to specify that you cannot have negative stock purchasing. Okay, so you can't have, for example, -1 stock A, or negative value B stock B. Okay. So you have to specify. This is a dumb thing for us human, but you have to specify this for solver. Okay, so we also have this. Okay, so we have to say, okay, A, if we show the number of a purchase of a stock A by just A, the A should be greater than or equal to 0. That means that it cannot be negative. B also the same. If we decide to show and represent the decision variable for purchasing how many of a stock B by just B, the B has to be greater than or equal to 0. That means that it cannot be negative. Okay? So we have these two type of constraints. The other type of constraints is equality. We actually don't have it in this specific problem, but it is a constraint that is used, type of constraint that we use. And our objective function or our goal is to maximize the total expected return for our investment after a year. So let's go ahead now and formulate the problem. So first of all, we're gonna, instead of just jumping into the modeling by mathematical formulation, we're gonna actually try to model it verbally for us to understand. Okay, so we wanna identify the objective function, different components of our model. What is the objective function, or what is the goal? We want to maximize the expected rate of return, the expected return after a year of our investment. And what are our constraints? For constraint, we usually use subject to, or for short, S dot T dot. So ST subject to. That means that our decision or optimization is subject to these set of constraints. So now we can actually verbally list the set of constraints. So one of the first constraint is the budget constraint. So our investment cannot exceed our budget, which is $1,000. Okay? The second constraint is regarding our investment on A. We said that we should not buy, and we must not buy more than $700 of a stock A. So that's our second constraint. The third constraint is our limitation on investment on a stock B. So we must not purchase more than $600 of a stock B. And the fourth and fifth constraints are just negative values. So you cannot buy negative number of a stock A or B. Okay, so we have 5 constraints, right? So now let's define our decision variable. Let's represent the number of purchasing, the number of shares of stock A by just A. Okay, so A is how many we want to buy from purchasing stock A. B is stock B. And now we're gonna start modeling. Okay, so what is the model? The model is to maximize the expected return. And return would be based on our investment on a stock A and a stock B. So what is our return for a stock A? That's how many of a stock A you buy, which is showed by A, multiplied by the price of A, which is $4, multiplied by rate of return in a year, which is 60% or 0.6. 6% or 0.06. Okay, so 0.06 multiplied by $4 multiplied by how many you buy from stock A. That's for a stock A. Plus, we also want to invest in a stock B. What is how to compute rate of return for that? So that's actually the rate of return is 9% in a year. That multiplied by the price of the stock, which is $6, multiplied by how many of a stock B you would purchase, which is just B. Okay, so your objective function is 6% multiplied by $4, which is 24%, multiplied by A, plus 9% multiplied by $6 multiplied by B. We usually call the objective function and represented by Z. Okay, so this is our objective function, and we want to maximize. Okay, this is the total rate of return, total return of investment in stock B and A in a year. Now let's write and form. This constraint is regarding our investment budget. Okay, so we cannot invest more on A or B stocks that would exceed $1,000. Okay, so how do you compute that? So how do you compute that? We would be each stock A would cost $4. Okay, so how much you spend on A would be the number of stock A that you purchase would be the A multiplied by its price, which is 4. So it would be 4A. For a stock B, it would be price multiplied by how many you purchase, which is 6B. So 4A plus 6B, that's your total cost of purchasing stock A and B. This should be less than your budget, which is 1,000. Okay, so this is your first constraint. Okay. The second constraint is regarding your limitation on purchasing stock A. How much you spend on a stock A, that's 4 multiplied by the number that you purchase, which is A. 4A should be less than $700. That's your constraint. The other constraint was for B. So that's the price multiplied how many you purchase. So that's $6 multiplied by B. 6B should be less than $600. And then 4 would be the number of stocks A that you purchase cannot be negative. So A should be greater than equal to 0. B also should be greater than equal to 0. So now we have everything here. Also, we know that A and B are our decision value, okay? So this is our model. The values that you see on the right-hand side of the inequality, for example, 1,700, 600, 0, and 0, these are called right-hand side shown by RHS. And the values on the left, such as 4, 4, 1, 6, 6, 1, these are coefficients. They are called left-hand side numbers. And the numbers that you see in the objective function, for example, 6% multiplied by 4, which is 24%, these are called coefficients, okay? So how to solve this problem? Well, to solve this problem, you might actually want to take your time to see if you actually can solve this problem just by, just give it a shot, okay? How much, how much of A and B should you buy so that your investment return after a year would become maximum? Just take your time to understand the model. If you learn how difficult this problem is, for example, for optimization, which is not actually, it's actually a simple problem, but not knowing optimization technique would make it pretty difficult to do. So I'm not sure how you would approach it if you don't know optimization, but I just want you to give it a shot to see if then when you learn optimization, you would appreciate the technique more. All right, so let's go to solving this problem. Since this is a small problem that only have 2 variables, A and B, there is actually a method called graphical optimization solution methodology. So solving graphically, which can only be used when you have 2 decision variables, because we work with 2-dimensional system. You could do that for 3. This if you have like a computer, you can try it in a computer, but it would be really difficult. So basically, we're going to use this only for education purposes. There is no other use to it, and only for when you have 2 decision variables. So why we should use, if the graphical method is so inefficient, why should we use it? Because there is actually an education advantage into it. You're going to learn actually the terms and also the problem. So let's actually do that. How do we start off? Again, we only can use the graphical method for problems that only have 2 variables. The first step is to find the feasible region. What is a feasible region? Feasible region is the region of variables for your decision variable, the values of decision variable, which are feasible given your constraints, set of constraints. Okay, so that means that, okay, what range of values for your decision variables are feasible? That means if you put it satisfies all the constraints. Okay, so to do this step in the graphical method, you need to graph or plot your constraint. So you plot, for example, each set of constraint, each actually constraint, and find which side of this constraint is feasible. Okay? And then you add the other constraint, and find, then after you have included all your constraints, you have to decide which is the common feasible region. If there is no common feasible region, your problem is infeasible, cannot be solved. All right, so after this step, after you find all your feasible region, you want to actually find your problem, solve your problem to optimality, find this optimal solution on the other hand. So this is actually pretty easy. What you need to do is find the corner point or feasible corner point. A corner point is the point that are the intersection of two constraints. For example, if this is like a plot of your problem, and this is one constraint and this is another constraint, the intersection between these two in the feasible region is called feasible corner point. Okay, so identify all the feasible corner points and then find the objective value for the values of these corner points for each variable. Okay, and then the corner point that has the highest value, if you're working with a maximum problem, maximization problem, that would be your optimal solution. Or in case of a minimization problem, the corner point that would yield the minimum objective value would be your optimal solution in minimization problem. All right, so let's start with our problem. You have two decision variable A and B. You want to optimize it. I have plotted this graph here for A. The x-axis stands for the decision variable A, stock A, and the y variable or y-axis is for the decision variable which is purchasing stock B. Okay. Now let's actually put our first constraint, which is our budget constraint. So this is our budget constraint. Our budget constraint says that which is $4 multiplied by how many of stock A you purchase plus 6 multiplied by B should be less than or equal to 1,000. So when you want to plot it, you don't go with less than equal to, you just go with the equal to. That would give you a formula of a line that you can actually plot it here. So this is that formula of a line. Okay. So this is that line, which is 4A plus 6B equal to 1,000. As you see here, for example, on the x-axis, where the line is intersected with the x-axis, that's actually A equal to 250. Okay? So for A equal to 250, 4 multiplied by 250 would be 1,000, which is equal to 1,000. So that means B should be 0, right? And you see that B here is 0. On the other hand, on the point where the this line has an intersect the y-axis, and there is where actually A is 0 and B is equal to 267, something like that, 266.67. Okay, so which side of this is the next step. Which side of this constraint line is the feasible side or feasible region? The one good practice here is to just find a point on one side and try to see if that's feasible for that constraint. Okay, so the constraint was 4A plus 6B less than or equal to 1,000. Okay, so I'm going to choose 0 and 0, A0 and B and 0. If you plug that into the constraint, which is would be 0 plus 0, which is less than 1,000. Okay, so that makes this point feasible. Okay, so the left side of this line is feasible. Okay, this is a feasible. Now I'm going to add the second constraint. So the second constraint was 4A should be less than or equal to 700. Okay. Because I want to plot it, I'm just going to ignore the less than. So I'm going to plot the 4A equal to 700. This is the line, 4A equal to 700. Which side of it is feasible? You can plug in, for example, 200 and 0 or 0 and 0. For example, let's try 0 and 0. Is 0 and 0 feasible here? So A0, that means 4 multiplied by 0 is 0. 0 is less than 700. So the left side of this is the feasible region. Okay. So now the common region is this common space between the constraint 1 and 2. Now it's time to add the third constraint. The third constraint was 6b should be less than 600. Okay, so this is the constraint. Okay. Which side of this is feasible? I'm gonna again try the 0 and 0 point. So 6 multiplied by 0 is 0, and that's less than 600. So the inside of this again would be feasible. So now the common feasible region, you can actually imagine what it is. It's this area here. This area. Okay. And the other two constraint was A should be non-negative, B should be non-negative. So again, this would be forget about the this extra line. This shouldn't be. So that's our feasible region. And these are our coordinate points. The intersection between different constraints. For example, this one, this guy here. Let me change the color here. Blue, for example. This is one coordinate point. This is one coordinate point. This is another coordinate point. This is another coordinate point. This is another coordinate point. Okay. Now that you have found the feasible coordinate point, for each point, you're gonna plug in the value of that point into the objective function and find the objective value for that coordinate point. Because this is a maximization problem, the coordinate point or the A and B associated with the coordinate point that would make the objective value maximum or has the largest value, that would be our optimal solution, which would be this guy. 100 and 100. All right. So let's do that. So we have 5 feasible coordinate points. The first one is 0 and 0, which is the intersection of constraint 4 and 5. What is the z value, the objective value of that? So that would be 0 plus 0, that would be 0. Okay, so that's 0. The second coordinate point is 0 and 100. So purchase nothing of A and hundreds of B. Okay, so this would be the objective value for this would be $54. Okay. The third coordinate point is the intersection of constraint 1 and 3, which is 100 by purchase 100 of A and 100 of B. This would actually yield $78 in investment rate return after a year. The next corner point is 175 of A and 50 of B, which is the intersection of constraint 1 and 2. So this would be $42 and $27 for investment in B, and that would be $69. Okay, so far, the third one, which is 100 and 100, would make the largest investment return. Okay. The fifth one, which is 175 of purchase 175 of A and nothing of B, would yield $42 in investment return. So the best one, the maximum one, is this guy, $78, which is purchase 100 of A and 100 of B. So we show that by A star and B star equal to 100. We show it by asterisk, and that's a symbol of optimal solution. Okay, so whatever decision variable you have, if it was X and Y, it would be X star and Y star would be 100 and 100. That's the objective, the optimal value. And Z star is the value of the optimal solution of objective function. Okay, Z star is equal to 78 for this optimal solution. All right, so let's recap our. We have 4 minutes left. So objective function, that's the goal that you want to, or a performance measure of your organization or system that you want to either minimize or maximize. In Excel, we call it objective cell. The objective coefficients are the numbers that you can see in the objective function. For example, 4 4a plus 6b, or 4 multiplied by 6% multiplied by a plus 2. That's 4 multiplied by 6%, which is 24%. That's coefficient. Constraints are the conditions enforced upon us by the system and the resources that must be satisfied. Right-hand side are the numbers on the right-hand side of the inequality. For example, 1,000, 700, 600 in our model. And the solution is just changing variable. We call it changing variable in Excel. Those are our decision variable. That's the value of decision variable. It's called solution. Feasible region is the region, the common region that, based on the values of a decision variable, would satisfy all of the constraints. That's called feasible region. Okay? And corner point is just any point on the intersection of two constraints, two or more constraints. You have another definition that's called binding constraints. So after you solve a problem or a model to optimality, if the value of optimal value, if you plug it into any constraint, if the constraint is equality, okay? For example, we had 4a plus 6b less than equal to 1,000, okay? So if you put the optimal solution value into a and b, and this constraint would turn into equalities, for example, it was 1,000 on the left side, 1,000 on the right side, then that would be called as a binding constraint, okay? So binding and non-binding is a state that makes sense after you have solved the problem to optimality. Okay, and that's our lecture of Introduction to Optimization. We are on the break, close to the break time. Any question before we go to break? All right, so we're gonna take a break and then come back after 15 minutes, 8 p.m. Okay, so you got it. Okay, so now that we learn about optimization, introduction to optimization, and we were able to solve a simple problem graphically, we want to move back to our own space, which is spreadsheet modeling, right? So we wanna actually try to see how we can actually use Excel to solve optimization problem. We're starting off with the simple problem that we had for investment. Okay, so let's just start with that problem. So, like the introduction to this session that we had, we talked about quality spreadsheet or quality modeling convention, a standard that we need to follow. We shouldn't jump right into modeling using a spreadsheet. Okay, so we need to think ahead, think forward. We need to think through the problem, the model, find the relationship, identify each part, each segment, and then a good thing that we learned is influence chart. Okay, so influence chart, we learned that okay, you start from the end and work backward. What is the end? The end goal for the objective function is the total return of investment after a year. So what influences those? We need to find all the factors that would impact that. We know that the objective function coefficients, which are the prices and also the rate of return, influence the return to total return after a year. So that's one thing. The other one is decision variable. That's A and B. How many stock A and B we purchased. That's also would define our objective function value. And also the constraints, the constraint coefficients, which would also impact the left-hand side. Okay, that's how much A and B you can find, given that you cannot purchase or spend more than $1,000. You cannot spend more than $700 to purchase a stock A. You cannot spend more than $600 to purchase stock B. Okay, so this is the relationship generally. So now we have it because we already solved this. We have a good understanding of the problem. So let's move on to the next step. Okay. So Excel has a powerful solver for a methodology, optimization methodology or tool to solve an optimization problem, which is an add-in. That means that it wasn't already built into it. It's something that they added. There were actually another company here, the Frontline system, they added in 1995. So it's not, because it's an add-in, you have to make sure that it's already loaded in your Excel file, okay? Solver is flexible in many ways. Why it's flexible? It can handle linear, nonlinear, and also integer problems. So it's quite effective if being able to solve different types of optimization problem. It can solve small or medium-sized problems. For example, as I said, the limitation to Excel solver is for the standard solver, which is the one that it's adding in our Excel. Is 200 variable, a problem with 200 variables and 100 constraints. So any problem bigger than that size, it cannot solve. It cannot be solved using Excel. And also, some cons of Excel. Excel is inflexible in that sense that, as you're gonna see when I model this problem, the model has to be specified or modeled, represented in a specific way, which is not convenient or probably actually practical for all sort of problems. So it has its own style that you have to put there, and it's more of a not user friendly if you have used more powerful tools such as Groovy with Python, for example. It's not as user friendly or as efficient as those methods. It doesn't give you much help in setting up your LP, so it doesn't come with like a helpful guide or how to set up your LP. You kind of have to understand it from somewhere, and lucky for you, we have this session, so we can learn it off. It doesn't scale well, especially if the decision variable have more than 2 dimensions. So, for example, if you had like multiple dimension, for example, 3 subscript or superscript, it's very difficult to put it in Excel. Unlike programming language, unlike, for example, YAML or AMPL or a combination of a solver with a programming language such as C++, Java, or Python, Excel would be super slow in formulating difficult problems with high dimension. The solver that the method or the algorithm that solver uses to solve LP, linear programming, is the one invented by George B. Dantzig. He was actually a professor at University of Berkeley, California, Berkeley. And the method was invented in 1947. He called the algorithm simplex method. And he actually died in 2005. He made actually a great contribution by coming up with this method, a great contribution. If you're just counting the billions of dollars that has been saved using this algorithm, and many other in many other areas that are non-economically, it's huge. It's very huge. All right. So how to find the solver, because it's an add-in. Okay. So if it's possible that by default it's not in your Excel representation, okay, or in groups in data. So let me actually close this off and go to another Excel file to show you where you can find it. Okay, so right now I actually have the solver. If you go to the data tab at the very end, which is the analyze, analyze group, analysis, data analysis. There is a solver. This is the solver that I'm referring to and we want to use. This is the solver for our problem, problem. But it is an add-on, add-in. So it's possible that you don't have it by default. So you can go, if you don't have it, this is for PC, probably very similar to for Mac and Apple. So you go to File, you go to More. If you don't have, if it doesn't show options here, you go click to More. It shows the option. You click on the options, comes this, shows this video for you. Look on the left-hand side and find add-ins. Click on the add-ins, then look for the solver add-in. The solver add-in, here it is. So hit the click on it, select it, and hit go here, and make sure that it is checked here. The solver add-in is checked. If it's not checked, make sure that it's checked, and then hit OK, and it's gonna be come here in the analysis group under the data tab. Okay. It should be similar for Mac, but I don't have a Mac, so I don't know exactly. But I was told that actually is quite easy.
I'm sorry, do you mind doing that again?
I'm sorry?
Where did you find the more option?
Okay, so click on File, go on the very down below of the list. Okay, there you can find more. You find it?
No, mine doesn't show the more option.
Okay, so see here, File. If you can't find options here, then click on More. You should have a More.
Mine didn't have more either. It was just in the, it's just in the options. You just have to press options.
Okay, just click option.
Okay.
Yeah, click option and then go to add-ins group here and then select the solver add-in. Hit go, make sure that the solver add is checked, and then hit OK.
Got it. Thank you.
Sure. Right, so let's record our model. So we have a investment optimization problem, which we wanted to, our objective function, objective or goal was to maximize the return, rate of the return of investments after a year. So we had two decision variables, A and B. A is stock A, B is stock B. And this is our objective function, which we want to maximize it. And we had a set of constraints, 5 constraints. This is the first constraint. Our investment portfolio should not exceed our budget, which is $1,000. Our second constraint was we do not want to invest more than $700 on a stock A. We do not want to invest more than $600 on a stock B. This is our third constraint. And our fourth and fifth constraint is just the non-negativity constraint over the decision variables. Okay. So how to set up this in Excel? Again, we want to follow the convention. So the best thing is to make sure that you follow my styles file. Okay, so try to open that file, and you can open up another Excel worksheet file and actually merge the style, or you can just in the same file save it, save it as another file. And then, because you don't want to damage the original file or make changes to the original file, so we can save that as another file, whatever model or problem is solving, and then just open up another sheet and a stock model. Okay. So you have to follow all the convention that we went through. Try to use labels. Try to specify your inputs, your outputs. Use the style bluish for the inputs. Red for decision variables and constraints. Also, make sure that you have the left-hand side, right-hand side, the range names, everything works fine. Okay. And then we're gonna add, after you have come up with your model, you can add it to your solver. Okay, so first, let me go ahead and open up an Excel file here that I want to model it. So please go ahead, open up Excel file and follow with follow after me and start modeling. Okay, try to be active. So this is where I put the comments. Continue to the comments. I'm gonna open up just another sheet, and I'm gonna try to follow all the conventions. So I'm gonna say simple investment model, or whatever other name your problem is. Okay. Here the same. LP linear programming. So here I'm gonna put the inputs. What is my input? My inputs. We had the price of the stock A and stock B, and also the rate of return. Okay, so price per share. Here I'm gonna put the stock A, and here I'm gonna put the stock B. Price per share for stock A was 6%. Okay, we can also use the percent. And for B was 9%. So now I'm gonna follow the convention. This should be the line to the left. It should be in the middle. And the other input was the rate of. This was actually rate of return. So, and this is price per share. So price per share. This was $4 for stock A, and $6 for stock B. Right. Okay. All right. So these are our inputs. So I'm going to use my input style here. All right. Next is our decision value. Decision value. I'm gonna copy these for stock A and stock B. This is going to be our decision value. Number of shares to buy. So you can, right now we don't know how much. For example, I'm gonna start with 0. You can start like put 0 here, or we can start another value, 1, whatever. This is what we want to optimize. We want to find the optimal solution for. This is my decision variable. Okay. So we put the input, a decision variable. Now it's time to put the constraints. Constraints. Okay. As I said, there's a special way to put a model into Excel for optimization. We could go with another way, but let's actually follow the same convention. So here I'm gonna actually put the constraint in different rows here. Okay, so amount invested here. One of the constraints was the amount invested for our budget. Okay, shouldn't exceed $1,000, right? So here I'm gonna copy a statement A and B to make sure that we follow the numbers correctly. Okay. So a stock for a stock A, we shouldn't invest more than $700, and for a stock B, shouldn't invest more than $700, and our budget was $1,000. Okay. So this cell should be a calculated cell. This is how much you have invested in a stock A. So you can actually calculate it based on the other cells. This is how much stock A you have multiplied by the price per share of a stock A. This will be how much you have spent on a stock A. Let me change this to 1 to show value here. Okay. And for this cell, the same. The price of the share multiplied by number of shares that we have. $1 and $6 right now. Okay, amount invested. And then this is our budget, or the maximum amount. Okay, maximum amount. This is where I want to put the right hand side. That's the $1,000 our budget, $700 for stock A, and $600 for stock B. So this is the limitation of purchasing a stock A. That's $700. And this is 600. We can also add a total here. So total is just going to be how much you spend buying stock A plus stock B. The same here. So here the value is $1,000. Okay. In the middle, the space in the middle, you can specify just for the readability purposes. You can actually, it's a good practice to specify the constraint inequality sign. So for example, we know that how much you have spent on a stock A should be less than equal to 700, which was our model. Let me bring out the model. Copy this. Copy and paste it here. Yeah. All right. So see, for A, how much you have to spend on stock A should be less than 700. So this is less than equality. So here I'm gonna put a less than equality sign. Where you can find it? You can find it in the insert, in the symbol up here. This is the inequality sign. Insert. So I'm gonna align it in the middle. Then I'm gonna copy that, because for stock B is the same, less than equal to, and for budget is also the same. Okay. All right, so that's our constraints. If you notice, I didn't put the fourth and the fifth constraint, which are the non-negativity constraints, because those are like default constraints that you don't need to specify here in the spreadsheet. You can actually specify it in the model, in the solver model or tool. Also, these are calculated cell. I'm going to leave it blank to follow the conventions, but these values actually are input. So I'm going to use the input style. All right. So there we have it. So I would if you could actually leave this here, this would really help. All right. Intentionally, I actually did not use the range name here because I want to add it later for you to see that one of the benefits after I add it. One thing is left here. What is the next step that we need to do? The other components of our problem, our model. What are we missing here for the optimization model? Anyone?
The constraints for being non-negative.
No, I said that we were going to add that in the solver function.
Oh, okay.
What is the other component of the model that is missing?
Output.
The objective function, right? That's what we want to maximize. That's one of the main thing, right? So how do you compute the objective function? That's actually the expected return. So I'm going to label it expected return on investment. And you could say how much is it for stock A, stock B, and then total. Here. For a stock A, how much you're gonna make on return? That would be the return, the rate of return multiplied by price multiplied by how much you have. Okay, so the rate of return for A multiplied by the price per share multiplied by the value of the decision variable and how much of A you purchase. 24 cents. The same goes for B. It would be 9%, the rate multiplied by the price multiplied by how many of B you purchase. Okay, so because this is like a live cell, a dynamic cell, I can actually copy it here, drag it, and do the same. So right now, when you look at it, it says C4 multiplied by C5 multiplied by C8, which is not a good practice. But as I said, I'm gonna add the range name later on to show you another important benefit of range names for labeling. All right, so let's compute also the total. So the total, the maximum, you want to maximize the objective function. That's the how much you make for stock A and how much you stock B. Then you sum them up. Okay, so it would be summation of these two values. You can also use the sum function, but these are just two values. I'm going to add them up. So this is the total how much you make on your total investment, and this is going to be our output, right? This is how much rate of return or the expected rate of return on investment. Total. Right? Okay, now our model is ready. The next step is to put this in the solver. Okay, so I'm going to open up the solver here. This is the solver. You see this window? The first thing here is set objective value. So objective cell. This should be reference or linked to your objective value or output here, which is this cell. Okay. All right. Now, do you want to maximize or minimize? Do you want to maximize? So I'm going to select this. By changing variable set, this is your decision variable. That's how many of a stock A and stock B you purchase. Okay. So this is the range of your decision variable. So this is a stock A and a stock B. So as you see here, it just shows nonsense, right? B6, B8, blah, blah. Okay. So that's your decision variable. The other component is to add the constraint. Okay. So this is where your constraint is going to be added. So you click on add, it's going to open up this. Okay. You can actually add individually, or you can add by just for actually more being more productive, you can actually add a range of cells here. So I can say that the amount investment, this is the amount invested. This should be less than equal to, so I'm going to make sure that this is selected as less than, and the constraint is the value here, maximum amount. Then I hit add. This constraint is already added. The second constraint is the amount invested on the left hand. Make sure that the less than equality is the same for this, and the right hand side will be $600. That's how much you can want to invest on B. Click add, and then that one is also added. The last one is for total. So I'm going to make sure that this is selected, which is less than equal to the amount, which is $1,000. And now hit OK. So if you look now, there are 3 constraints here shows B11, C11, D11, less than equal to all of this. Okay. So our constraint has been added. But there is another way actually I can do that. So instead of just adding every constraint one by one, you can add a range of them. Okay. I can say, okay, all of these 3 values should be less than equal to all of these 3 values. Then I hit OK. Now it is shown as just one set of constraints. Okay. All right. So the next one here, there is something you can check. It says make unconstrained variable non-negative. This is the non-constrainty or non-negativity constraint that I was talking about. Okay. So because we have that in this problem, we have to make sure that this is checked. Okay. So if you check this, this is where the 4th and 5th constraint will be added into the solve that we didn't add it here. Okay. All right. The next component of this solver is selecting a solver method, a solution methodology. Because we are using a linear programming problem, this is a linear program, we want to use the simplex LP problem or methodology, simplex, right? Now there is 3 button here. You go just hit the solve and see what happens. Okay, look at my model right now. So my model for decision variable, I have one stock A and one stock B, and the profit is 0.78. Okay, so when I hit solve, it's immediately in an instant it's going to solve this problem. As you see here, the values changed. For a stock A, it says 100. For a stock B, it says 100, and the total expected return is $78. Right? So now in this window, there are a couple of options for you. You want to keep solver solution. If you want to restore the original, you can click this one. And on the right hand side, you can actually ask solver to print out for you the answer, the sensitivity, and the limits, or none of them. Okay. So right now, and also if you click on this, when you hit OK, it's going to return to the previous video, which I don't want this to do that. Okay. So let me hit OK. So this is what happened. This is our optimal solution. That means that the best investment would be to purchase 100 of a stock A and 100 of a stock B, and with that investment plan, you're gonna make $78 in investment return. Okay. All right. So again, let me open up the solver. So you see here, everything is in just nonsense cell references, okay? Because I didn't use the range names. Now let me close this, and now I'm gonna use the range names, okay? So the range names that I use here, I can actually use a range names for several cells with the same label. For example, a stock A and stock B, these are for rate of return for a stock A and stock B. So if you go to the formula and create from selection, make sure that the left column is selected. Now, both these 2 values are called rate of return. So it's like a list or a matrix. Okay. I can do that for this cell as well, and this cell as well, and this cell as well. Okay. And another important one is here. I can put because I can't put it on the left side or above it, I have to put it somewhere either below or on the right side. So I'm going to put it on the right side, and that would be expected ROR, rate of return, expected return. Yeah, R would not be a good thing because it would be not too much abbreviation. So expected return, now I'm going to select this cell and go to the create, make sure that the right column is selected. Now hit OK. So now go ahead and open up in the data tab, go ahead and open the solver. Now see what happened. Everything now, he uses range names and it makes totally sense. So the objective is expected return. You want to maximize expected return, and the decision variable is number of shares to buy, and the constraint is the maximum amount. I didn't select these. Go back to the formula, add these as well. Now I'll go to the data solver. So look at the constraint. It says amount invested should be less than equal to maximum amount, right? So this makes sense. It's much better than just having B13 to D14, right? Any question? All right, another thing that I wanted to show you is the report. Okay, so the report, if you click on the answer report just here and I hit OK, it's gonna look at the number of sheets that I have. I have simple investment model and another sheet one, and there's no other sheet. If I hit OK here, it's gonna create another sheet here for me. It's called answer report 1. If you click on it, it's gonna look like something like this. Okay? So these are just some description about the problem and model. And if you come down to these tables, it just shows you about the problem and the values that you have. So it says the objective cell, your maximum, it's a maximization problem. The cell, the objective value is in cell D16, and its name is expected return. The name is expected return. The original value was 78. Actually, it was 0.78 because I rerun this. It shows $78. But if it was the first time that I run it, and I only had this stock A1 and stock B also 1 or 0, it would show the objective value, the first objective value here. And the final value, that means the optimal value, would be $78. The next table shows the decision variable. It says that the number of shares to buy stock A is one of the decision variable. The other one is how many stock B should be purchased. The original value, it shows again 100 because I rerun this, so it was run again by 100. And the final value is 100 and 100. And under integer, it says continuous because this is not an integer problem; it's a continuous problem. It is a integer problem, but in this problem, we actually relax the integrality of the problem because it's beyond the scope of this course, but we can do that for this specific problem. All right, on the last table, the third table, it shows your constraints. Okay, so we have 3 constraints here and 2 negatively constrained. The amount invested in stock A, it is in cell B11. The cell value is 400. The formula is here. It shows, and also for stock B and total. And on the last 2 columns, we have a status and a slack. Okay. So under a status, the first constraint is said not binding. That means that the amount that you have invested for stock A, it doesn't exceed the $700, or it's not equal to the $700 that maximum amount that you will specify. Okay, it's less than that, which is actually 400, right? So right now it's 400, but the maximum was 700. Okay. So because 400 is not equal to 700, it's not a binding constraint. But the 2 other constraints, if you look at, The second constraint, how much you invest on stock B. The left-hand side is 600, and the right-hand side was also 600, and that was your maximum amount spent or invested in a stock B was 600. Because 600 is equal to 600, that's binding constraint. Okay, so this is binding constraint. You have 0 slack, and also for the total budget constraint, the values on the left-hand side of the inequality sign is equal to 1000, which is equal to your budget 1000. So that's why this is also a binding constraint, and there's no slack. That means that you cannot spend more. There is nothing to spend. All of your budget has been used up. All right. Any question? Let me stop share this. But we have a lot of time here. Any question?
Professor, do you mind going over how to do named ranges of multiple cells at the same time
Yeah, sure.
again? Thank you so much.
All right, so it's pretty simple. No matter how many columns you have, I have the labels here, or the names on the left-hand side. Actually, Excel can automatically sometimes identify whether your labels are on the right side or left side, because if you have values in the right side. So if I just select all these, and also this, and also this, and also this, okay, and you go to the formula. Right now, if I just click on name manager, it shows all the name range that I have used. I can actually delete all of this. I can delete all of this and then add the data. So right now there is no name range. Okay, so none of these have name. We can just select those cells that we want to range name them. So this is the maximum amount, 700, 600, 1000. And also this is the expected return, but this is actually different system from this one, because all of these that I have selected, the name is on the left column or left cell, and the values are on the right cells. But this one, the name isn't on the right. Okay, so I'm not gonna do this one now. I'm gonna do all of those at the same time. Okay, so left column, hit OK. And for this one, I'm going to select it individually. I'm going to create from selection. See, automatically it says right column. That means that the name is on the right side. Okay, hit OK. Now go to the name manager, and you see all of the names are listed. Okay. So this name range is different from what we have done before, because this rate of return is actually a list which contains 6% and 9%. It's not one value. It's not a name for one cell. It's for multiple cells. Okay. So price per share, it's actually an array. Okay, which contains $4 and $6. Right. For example, the amount invested. This is a name range for 3 cells. Okay, it's for stock A $400, for stock B $600, and for 1000. This is only this is only good for solver. Okay, it shows here, but not for the previous modeling that we used. For previous modeling, every cell should have its own name. Right now, if you click on this, you see that the name of the cell hasn't changed. This is still B4, this is still C4, this is still B13.
Thank you so much. I was confused by the array aspect.
Okay, so let's go back to the lecture slides. So this is just description of what we already did in Excel. So I'm not gonna go over all of those. By the way, LHS stands for left-hand side, RHS stands for right-hand side, and left-hand side is just the values on the left side of the inequality in your constraint. Okay, so if I go to these constraints, it is your model here. This is the model. You see the set of constraints here. This is the. It is not a good color. Okay, this is the set of constraint inequalities. The left side of these values 4, 4, 6, 6, which is a matrix. These are called left-hand side, LHS. And on the other hand, the values on the right are called right-hand side, RHS. Okay, so these are RHS. Okay. This also shows the where you put the models component in your solver window. We're gonna skip over this one as well. So if solver for some problem, if your problem is infeasible, that means that it doesn't have any solution that would meet all your constraints, okay, or satisfy all your constraints. Then it would actually give you a message that your model is infeasible. If it's feasible, then it's gonna show you the optimal solution. And you are able to print out the answer report and the decision variable as I showed you in the Excel file. The table that shows the decision variable values, how much were they at the beginning and how much are in the final solution. Also, the same goes for the constraint. It shows you the left-hand side, the right-hand side, whether they are binding or non-binding, and how much slack you have. We could also print out the sensitivity to report. We don't have time to go over that. That's also another table that we can do. That's actually, again, in a step. So your optimization approach or effort is not going to end by just finding the optimal solution. There is another step after that, which is a very important step, and that's actually the analysis that you need to do after that. It's called sensitivity analysis. This is where you want to see how much your objective function is going to change your optimal value. If you, for example, change your, for example, if I want to see if I, instead of $1,000, if I invest $1,100, how much am I going to get? Or, for example, if I invest in $900. Or, for example, if I change my mind and said that, okay, instead of $600 cap on investment on B, I want to set it on 900. Okay, so you want to see how, what would be these changes would affect your optimal solution for decision making. The sensitivity analysis is an approach, right approach to do that. Or any other what if scenarios. For example, what if the price of stock A, instead of $4 jumping to $5? How much, how would that affect and impact your decision making and optimal solution, and the rest of it? So we're gonna do more of this analysis and sensitivity analysis next week. Any question? We are actually done with our lecture. Discard. Any question? All right, thank you very much, everyone. Have a great weekend, and make sure that you don't miss the assignment. It's due Friday night, like one night from now, the first assignment, and the next assignment is also posted and is due next Thursday, right?